Welcome and thank you very much in your interest in my presentation today. I will be talking about the vision platform approach, rethinking line scan systems. So my name is 𝗏𝗂𝗓𝗏. I'm the head of R&D at Chromasense. And yeah, I would call myself a line scan expert. My background is in physics, optics, data processing. And today I'm here, the team manager for the R&D team. So we as Chromasense, we are line scan and industrial imaging experts already since 1992. So we have a lot of experience in many different applications. And part of that I want to show you today here. So the company was started 2004, formerly 𝗀𝗍 Siemens. Today we are about 90 employees. So we are quite focused on R&D innovation. So half of the team is from R&D. We are a member of the TKH group since 2018. And yeah, we focus on high performance line scan cameras and image capturing system in general. And also LED light, as we also will see later, is very important to us since our experience tells us light is really the key. It really matters. And we have a strong customization background. So Chromasense comes from, let's say, 100% of customizing. Today, it's still a substantial part of our business. So we do a lot of special vision modules with integrated light image processing, special optical systems. So we are really expert in many different use cases. So what is a typical approach to a machine vision project? So typically it starts from what is the size of the object, what kind of defects we have to look at, what is the size of the defect, it tells us about the camera resolution, what is the cycle time of the machine I have to integrate the camera, which are the surface properties, if it's a glossy or a more matte surface, what kind of material we have to inspect, the defect type, then we start to acquire the first data when we have our first vision system configured. We start the image processing development, and then we have some improvement cycles to really have the ideal output of our vision system and start deploying the first system into the field. And yeah, typically with the software improvements, there's also improvements later on after deployment into the field. So maybe it's not so common for everybody here in the audience to use line scan cameras. So I want to have a short view on where to use area scan cameras, the typical ones where you have an area sensor, and where to use line scan cameras, which have a line sensor. So if we look at an area camera, which are the pros, let's say on the positive side, with a single shot, you acquire the whole image, the whole area. It's quite easy to get started to get the first image because most of USB Ethernet interfaces, it's very quick to just connect it and you have already the view on your sample. It's easy to align because you have a live view. You can align the camera really with angle and positioning to the object you want to image, and you have a huge versatile offering on the market. Let's say on the negative side, if you have a moving object, so you will have a blur because typically integration time are longer, or if you have a rolling shutter sensor, you can have quite severe negative impacts on the image if your object is moving during image acquisition. And if you go for really high resolution, if you need really a lot of pixels, let's say, to image your object in the required resolution, it can be really expensive. And if you want to image or let's say measure a 2D surface, you have a 2D, let's say, reflection geometry. You have from the light source incoming angles and from the camera outgoing angles of the light, and it's a two-dimensional problem. You see that the angles are changing over the area, and as we will see, it's different if you have a look on a line scan camera system. Talking about line scan, which is on the positive side, you can do an endless acquisition on moving objects. So we show here if the object moves, a line scan camera, it takes line by line, and you can run it 24/7 and have a huge image, for example. You can run these cameras on short integration time so you reduce the motion blur. And you can have really high resolution system, let's say at affordable system cost. So you can have up to 16K or 15K long sensors. And yeah, you can acquire like 16K by 20K. If you want to buy, let's say, an area sensor with that resolution, it's really, really expensive. And let's say the illumination and reflection geometry, it's a one-dimensional thing. So you have the light coming in from one side, being reflected on the other side. And let's say in transport direction, you have a repeated measurement. So the angles are not changing in transport direction. Let's say on the negative side, you have to control, let's say, the movement of the object very precisely. So you typically have a high resolution encoder system really to sync precisely the movement of the object with the line acquisition of the camera, because otherwise you cannot have square pixels and your image will be, yeah, if your object even stands still, it can happen in a machine, you would always just image the same point. And of course you want the camera to stop. So you need the information from the movement to the camera. And yeah, there's also a challenging part, let's say, if you want to align the camera, because you only see a line and you don't have a picture. It's not so easy to understand where the camera is actually looking at, if the image is focused, if it looks nice. But as we will show later, let's say, there are means and ways to make that easier here. So yeah, having understood that, let's have a closer look on, let's say, typical line scan use cases. Yeah, pretty often you have something like web, because if you have a roll-to-roll web production process, it's quite straightforward to use a line scan camera because the object in the machine is moving anyway. So processes like paper production, foil production, but also print inspection is very important. You have offset, inkjet printing or intaglio, where the object is moving in the printing machine and you need a high resolution at high speed, and also your line scan cameras are used. Sorting applications, wafer inspection, and PCB and glass here line scan cameras are used because you can really have the high resolution with a line scan, and maybe adding even 2, 3, 4, 5, 6 cameras in a single system, you can have a huge field of view really at high resolution. For example, up to something like 8 micron pixel resolution on the object if you still want to have some overlap of a camera which has a size of, let's say, 100 millimeters. And glass inspection here, pretty often many different light angles are used to inspect maybe the backside of the glass, if there's a defect in the glass, on the surface. And here it's easier with the line scan camera system to have many different illumination angles in a single scan. So for example, if you look for print inspection, you can have a field of view of 1 meter, typically targeting something like 200 dpi. So you could end up with a configuration of 2 4K cameras or 1 8K camera. And so here you would have already like 2 4K cameras, and using 2 cameras with a less resolution helps you to reduce the system height. And maybe you also can split the data bandwidth on 2 systems. If you go for PCB inspection, typically this application target on higher resolution, like 10 micron per pixel, for example, like field of view of 600 millimeters. So you would need already like 4 15K cameras. So you see here like a multi-camera arrangement is quite important for these challenging applications. So how we start here. So if you have understood your application, you can start to configure the camera and the lens. You can have a multi-camera alignment, and then you have, of course, to think about the light arrangement. You can have versatile light options like dark field, bright field. I have a closer look soon on what that means. And of course, we need a rigid mounting frame for the whole system, to enable these challenging applications. So, and what is key here, as we have learned, is if you have a set here of 6 cameras, you want to have them perfectly aligned, that they more or less behave as a single unit. And you have like angles in many directions. You have the angle in the XY plane tilted, or you can have the camera tilted like that. You have the focus of the plane. And yeah, here it's really important to have a precise alignment to reduce the effort on the image processing side. You want to have the image being received from the system being as good as possible. So, and what we have done here really to simplify how to set up this quite complex system is we have designed a nice camera alignment adapter, and we have a software which runs together with a camera alignment target, and then the software evaluates from line positioning and from contrast of sharp lines or narrow lines. You can evaluate the focus over the field of view and slight angle changes, and also the resolution. So you have here, with the combination of this set of hardware and software tooling, the perfect toolkit to make a perfect alignment of a multi-camera system. And it really makes life a lot easier. So again, here on a bigger view, you have the pixel position in pixels on X, Y, Z. You have angle, a rotation on the Z-axis, and you have a look on left, right on the resolution, which tells you if the camera is tilted overall, and also you can align it for resolution, or here modulation, which is a relative measurement of MTF. You can have, let's say, the maximize the values that you know the camera is in best focus. So yeah, if you apply all of this, then you have a perfect aligned system, but definitely you're not done yet. So how to configure, let's say, the ideal system is also not that easy, to find which lens, which adapter, which camera type. So also here, to make life easier, what we have done, we invested quite a lot in a nice online configuration tool where you can put in, let's say, which are your spectral requirements, color, mono, or even shortwave infrared, which camera interface you're targeting for, and you can add the geometric restrictions or requirements of your system, and receive from the system a lens recommendation, and also the full mechanical outline of how to position the cameras, which are the distances, the depth of field. So you get a perfect configuration just starting from your use case requirements, like field of view, the speed, and depth of field, for example. So, but still not done yet. When you have the perfect lens, a multi-camera system aligned, we have to think about which is the ideal light source, and really light matters. This is what our, or at least also my more than 10 years experience in that field shows me, that light is really, really important. So, and let's say in an ideal world, we can think about two perfect surfaces, let's say. On the one side, we can have the perfect mirror, where an incoming light beam is reflected perfectly at the same angle with respect to the reflecting surface, and let's say all of the light is reflected in that direction. Or you have a perfect diffuse surface, where, let's say, the light impinges the surface and is scattered in the whole half sphere from the diffuse surface. It's the ideal matte surface, and let's say the reflection is completely independent of the incident angle. So it's, let's say, you have these two worlds, but in real life, we live somewhere in between. Especially if you do not have, let's say, a perfect mirror, which is used for maybe optical applications, you always have a scattering component. So that means if you want to describe a real life, a real world surface, it's a very complex function where you have to really describe, dependent on the incoming angle, how much light is reflected, how much is scattered in which angle of the half sphere. And of course, this is very, very difficult to describe, and so the more or less only straightforward way is, of course, there are models in between where you can model surfaces, which is also used for computer graphics, but also pretty often we use measured data. And just for an example, here is a BRDF database from the Mitsubishi Electric Research Laboratories. This data can be used for modeling of surfaces, understanding of surfaces, but all of these are based on measurement. That means if you have all these different surfaces, we really have to think deeply about which is the right configuration to illuminate these surfaces. So we have to deeply think about different possibilities for illumination geometries. So which are the typical ones? What we call dark field, where you have, let's say, if the camera always looks straight down on the surface, and the dark field, you have typically a 45-degree angle, or let's say a flat angle, and let's say the direct reflection will always, let's say, pass the camera. But what the camera sees is only, let's say, the diffuse component of backscattered light. So if you have a strong diffuse surface, you get a lot of signal. If you have a more or less perfect mirror, signal is very little. Then pretty often a tube or dome light configuration is very useful, where you have the light coming in from a large set of angles, more or less the whole half sphere preferred, and the camera still looks at one angle, and we will see soon in which application this can help. Backlight situation, if you have a semi-transparent foil or material and you want to see all glass inspection, then of course it makes sense to have a backlight situation, to have just light coming from the back. Or you have a coaxial configuration where you want to have the light coming perfectly from the same direction as the camera looks on the surface, and then you see also direct back reflection strongly. Or the bright field, which is very close to coaxial, but you have, like, let's say, incoming and outgoing angle use. So you tilt the camera and the light source to get signal back from a reflecting surface. But yeah, besides, let's say, these typical geometries, we can have quite some more. For example, you can, or what we have at Chromasense is we have a different set of dark field illumination. You can have C focus, which is a medium focus for, it's very good if you need a high homogeneity, also with the changing distance of the object. We have a defocus dark field, which is colliminated more or less, so it goes parallel, a parallel beam, so you can place the light source quite far away from the object, and it's also quite broad, let's say, illuminated area, so it's less sensitive for alignment between camera and light source. Or we can have a stronger focus light source if you need really high power on the surface, and like semiconductor inspection or inkjet print inspection, where also the surface distance to the camera is really well controlled. And we can have, for example, the coaxial dark field. It's quite special one. If you want to look into a pocket, for example, we can have a directed light through a beam splitter mirror looking into the module. And for bright field, we can have the typical coaxial configuration just explained. We can have the bright field, so we don't have the beam splitter, which always costs quite a lot of light. And we can have the coaxial focused version, where we have like a focus in one direction and diffuse in the other one. And it's very helpful if you want to have a coaxial light situation at high resolution, when you need a lot of light. And again, the backlight situation. And we offer, for a tube light, there's also different use cases. For example, you can look perpendicular into a tube or at an angle of 15 degrees. Why does it matter? Imagine if you have a direct back reflection from the surface here, in the 15-degree angle configuration, you will have a strong bright field component from the diffuse part where light is coming into. But if you look perpendicular through the tube, let's say where the slit is, where the camera is looking through, there is no light coming from this direction. So it makes a difference if you look at 0 degree. So you have the direct back reflection on a plane, on a perpendicular surface excluded, whereas if you use an angle, it's included. And for quite challenging applications where you need actually a set of all these light combinations more or less together, we have designed what we call a combined tube light, where we have, for example, you can have red light diffuse from more or less all angles. You can have a flat angle dark field component, which can be, for example, here green LEDs, and you can have a blue bright field component. And so you can use a color camera to split the 3 incoming light angles on the 3 color channels, and then you have, within one run, within one scan, you have 3 different illumination geometries. And for really challenging surfaces, this is, and if you have to take care for different kind of defects in inspection tasks, it's a very useful configuration. So, but as we have seen, like, surfaces, how they reflect light, they're so complex, so we cannot describe them in an analytic way. We have to approach it experimentally. So what we have done, we have thought about which are, let's say, driving applications in vision market, or for us maybe also in line scan, and which are, let's say, the application fields, for example, like archiving digitalization, where we have something like wood, print, stone materials. We have print and packaging, electronics industry, electronic semiconductor, and we have samples of all of these applications which have optically completely different, but we have all of them really now on one target, and we can scan them with all of our light sources and make this data available that you immediately can decide which light source is the best for my use case. So just some examples, if you look into it using a dark field light, for example, here, this is a ball grid array. This is a small metallic spheres, solder paste or a solder, and you see you have strong back reflections on the edges. But you have a high contrast, for example, on a more diffuse organic material like rice. And again, here it's pilled in a plastic packaging. You have strong back reflections. And on a diffuse surface, it really looks, yeah, it's a nice color image here. With the tube light, it's completely different. You don't have strong back reflections, but you also have less contrast on the rice. But you avoid strongly highlighted back reflection because you cover all angles, and it's not just like the light is coming from one direction. And for example, for the coaxial, it's also very impressive that, yeah, you reduce also sort of contrast on let's say, more organic material, but you can also enhance a lot of microstructures on a back reflection on the substrate. And so again, here it shows that it can have huge impact on the what kind of light source you use for the use case. So, and just to emphasize what I just briefly discussed, we do a direct comparison of the three light systems. And for example, if you look on a piece of wood, if you go in, the images are quite similar. You can see you have, for example, here maybe less contrast on these color changes, but also more shadowing on, let's say, where you have like small cracks in the wood. And if you, for example, also if you want to look down into the pockets, it really makes sense to use a coaxial configuration. If you want to have, let's say, the illumination being independent of the surface shape of the object. And so here you can see it's not too much impact on it because the wood is very diffuse. So as we have learned earlier, the incoming angle does not have a strong impact if you have a diffuse surface, but you can see more back reflected light or stronger illumination on pockets. But it's a completely different story. For example, if we have here a glossy print with the dark field and also with the dome light, you have a good color representation of the print, but it's a completely different story if you go on the right side here to the coaxial configuration, because then you have predominantly the direct back reflection of the surface coming back to the camera, and you have a reduction of the impact of the color, of the diffuse part, the diffuse scattering of the color inks on the paper. But for example, you can see here the scratch. And it's a typical use case that, for example, if you want to see the color representation, you use a dark field light source. But maybe in the same system, you want to see if the coating, the glossy part, is really perfect. And then you have to go for a bright field or coaxial configuration. And both show you different properties of the object. Also here, I think it's a really nice example. If you look on the BGAs, you have strong back reflection on the edges with a dark field, and you have a strong emphasized microstructure on the backside on the substrate itself if you use the coaxial illumination. So yeah, it's really impressive, and I will also show later that it's possible to combine all of the three, which is required to cover the full application in total. And PCB inspection is also a very important use case. And also here we can see we have diffuse plastic parts and we have the metallic surfaces. And also here it really makes sense to choose the light source properly dependent on what you want to look at. Connectors are very challenging because you have a deep pocket to look in, you have metallic reflection. So also here the right choice of light source matters. And also here the dome light, for example, can do a great job. For a processed wafer, again here in the dark field, you can see like little spots contamination. They produce like a backscattering. But if you want to see really how the process structure looks like, you need a bright field component. So also here it makes sense to combine both illumination geometries, and I will later show that this can be done by a time encoding using a flash operation of the cameras to acquire both geometries at once. And rise, we showed this earlier, you have a huge change in contrast depending on the illumination geometry. And here it's also important to think about what you want to see and what you want to detect. Also very impressive, the glossy surface. Here it's so clear that the dome light does a great job to highlight that all features are visible, but the strong back reflections are suppressed. Metallic surfaces, also here, it really depends. You have an inversion of contrast, for example, for this defect. If you go for coaxial or dome light, in the dark field, maybe you also can see like only backscattering parts. And here it makes a huge difference, the illumination geometry. So I want to quickly talk about some very special use cases. Let's say I teased them already a little bit earlier, but for example, the BGA, the ball grid arrays, it's very important to inspect them for presence and size and quality. You can imagine if a processor is already in the factory done to 99%, and you want to solder it to your PCB, and you would really destroy a lot of money if one of the solder balls is not perfect, and then your whole PC is not working just because of this one little solder ball. So what we have done here, we have a flat dark field. The dark field helps to see some contamination on the substrate. We have the diffuse dome light, tube light, which helps to see really the shape of the ball, especially also with a 3D camera, which we also offer. And you can have the bright field component to see the structures on the substrate. So in here we combine all of this geometries in one module. Beam shaping. If, for example, if you have you want to inspect a wafer, you need the bright field component, and you need really a lot of light because you have high resolution. You have maybe to close the stop as much as possible to enhance depth of field. So there's really light is critical. And so we have developed a special light source which has a directed and a diffuse part. And you can see, for example, like without the beam shaper, you will see the distribution of the LEDs in the system, but with a special beam shaper, you don't see them anymore. You have a well-distributed homogeneous illumination, and we can enhance the signal by a factor of 20 compared with a, let's say, typical approach. Also what is very common if you have, for example, like a glossy window or packaging and you do not want to see this, we can use cross-polarized windows on the light source and camera side to suppress the direct back reflection. That can help a lot in many applications, and this is also possible in our, let's say, building block system of light sources. LED flashing, I explained earlier that for many applications, for example, like wafer inspection and others, it's really important to have a dark field and bright field, maybe with white light in one scan. So what we offer here is our LED controller can do, or let's say the combination of camera and LED controller, they can have a line-by-line synchronization. That line by line, the different geometries are acquired. And later on, the images can be deinterlaced. And then within one scan, one run, 2 illumination geometries are acquired with a single scan. This can be very helpful, and we can, for example, go up to 4 different geometries in one scan. So, we can have from all these building blocks of cameras, resolution, lenses, and light sources, there are so many different options. And just to give you a feeling, what can be done with the building blocks, and you can have only dark field for print inspection, like these two. You can have for challenging ones a combined dome light with a camera at an angle, or you can combine dark field and bright field with a focused bright field, or you can have a fully diffuse bright field. So there's so many options. And therefore, it's really important to think and test properly and understand the surface or the object you want to detect, and also how the optics behave to configure the ideal system. And yeah, we are more than happy to help anybody and to discuss who needs some support here to configure the ideal system for the present use case. So we can, for example, have up to 4 light conditions in one module with a backlight to dark field, bright field, and for example, flash them, or we can also configure them with RGB or near infrared, and to more or less enable most of the use cases. For example, also shape from shading can be done with these kind of setups. It's very versatile. So I'm always impressed myself how many possibilities we have, but it's really what we have learned in the past years, that it's so important to have many possibilities to cover more or less any application you want to target. So we are part of the TKH Vision group. So you have here, for example, Allied Vision, Chromasense, LMI, 3D, Microtron for high speed, Nerian also for 3D cameras, NET with their embedded area scan camera solutions, SVS Vistec with the high-end cameras, and Tatile focusing on smart traffic cameras. So it's a great environment here. It's very inspiring, and a lot of innovation around, and different views and different products for similar or completely different use cases. That's really what makes it so interesting to be part of the group here. So thank you for your time. I hope it was interesting listening, and I'm looking forward to receive your feedback, contact, or further discussion on use cases, camera geometries, light geometries. It can be myself or our very competent field application engineering team. Don't hesitate to get in touch with us. Thank you.